Hello and welcome to another episode on the calculus series. Today we're going to be talking about indefinite integrals. So we've covered derivatives pretty much, and now we're going to look at the other big kicker in calculus, the integral. So the integral, if you have an integral like this, so it's kind of this crowbar-esque S shape, but it's a little bit bigger, like so. This is kind of the inverse of the derivative. An indefinite integral is also sometimes called the antiderivative. So if you have a function f, for example, and you know its derivative is, say, I don't know, x squared, then an indefinite integral tells you what the original function must have been, right? So here you can probably think this through. So if I differentiate to get x squared, well, if I differentiate, then the power gets reduced by 1. So the power must have been 3, because if I differentiate, then the power is reduced by 1. So it must have been 3. And then I still need a constant, because if I differentiate it, I get 3x squared, but I don't want 3x squared, I just want x squared. So we have to account for that the power kind of jumps in front, right? So here the power 3 would jump in front, but here I have 1. So I need to multiply by 1/3. And you can always check that you've done it correctly by differentiating this one. If you were to differentiate this one, then indeed you would get 1/3, the power jumps in front, times 3 times 3 minus 1. I'm doing this quite expansively to illustrate the point. So this 1/3 times 3, those just cancel out. 3 times 1, that becomes x squared, and that is correct. Now, there's one little bit of nuance here that I've left out, and that is that this function could also have been, for example, 1/3 x cubed. That remains the same, but I could have also added 1, or subtracted 2, or something like that. Right? I could have added some constant c, because when you differentiate, that vanishes, right? So in fact we end up with a whole range of functions for different c's, like so. Alright, but here I was a little bit willy-nilly on the details here. I kind of pulled it out of thin air, but there's actually a formula for differentiating polynomial functions like x squared and like x cubed and regular x, and it goes like this. So if you want to differentiate a function, you'd say that the function is f prime of x, and then you have the regular function f of x, and then you have its antiderivative. So you have its derivative, that's that way, and its antiderivative goes the other way. And sometimes you'll see this written like this, so with the crowbar and f of x, and then to close off where the integral stops, you put dx or d theta, if you have a function of theta or whatever variable you're integrating with respect to. So you can write it like this. So this would be the integral of f of x, or rather the indefinite integral. But you can also write it as capital F of x, like that. So, but I'm going to be sticking to this notation because it will come in handy later, and you'll see this a lot. Alright, so now let's take a look at some integral rules. So I've compiled a list of 8 integral rules that are really the basic. They're pretty much just the basic. They're kind of the inverse of the derivative rules, right? So the first rule there, this one's pretty straightforward. So if you have a function that's, for example, 3 times x squared, and you want to integrate that, so you want to find its the function that when you take the derivative, you get 3x squared. Now this is x cubed, obviously, but we don't know that yet, right? That's what the integral is for. Then you can, first of all, you can take out this 3. So if you have some function of x multiplied by a constant, then you can just take this out like so. Like that. So that's the first rule. So a little more generally, so if you have k times some function f of x, and we integrate that. This rule is basically the same for derivatives, right? then you can just take the constant out of the integrand. Alright, so that's rule 1, pretty simple. Rule 2 is also quite straightforward. It's also the same for derivatives. So remember, if you have two functions f of x and you add onto that g of x and you want to find the derivative of them both, like of their sum, then you can just find the derivative of the first one and then add on to that the derivative of the second one. This is no different with integration. If you have the integral of f of x plus g of x, same with subtraction, by the way, that doesn't matter, and you do that, then it's the same as the integral of f of x dx and g of x dx. I think this one's pretty intuitive. It works the same with derivatives and it's quite straightforward. Alright, so these are a bit more general rules, like they have to do with functions and everything. So now let's take a look at a more exact rule, if you will. Alright, so a more exact rule has to do with what happens when you have 1 divided by x. Right? So what function do we have to differentiate to get 1 over x? Now you may remember this is actually the natural logarithm of x. So in fact the integrand of the integral of 1 divided by x is the natural log, and here I have to be a little bit careful because I have to actually put in absolute value of x here, like that. And then to be a little bit more exact, I have to also put in the constant from before. Now you might be marked down for this if you don't write down the constant, because it could technically be there, right? Right, so this is another rule, so let's do another one. I'll do a little bit of examples later on, show you how they work. The other one we already kind of saw, it's x raised to some power, or just some polynomial. And so first of all we have to increase the power by 1. Remember, by differentiating, the power decreases, so the antiderivative power increases, right? It's pretty symmetric. And then instead of multiplying by n, I have to divide by n plus 1. So I have to divide by the new power, right? Alright, and add c, like that. So this is kind of the equivalent power rule. I'm just listing them off here because they're kind of they're pretty much the inverse of the derivative rules. Same goes for if you have an exponential function a to the x, then instead of multiplying by the natural log of the base, you divide by the natural log of the base, like that. And the same thing if you have the integrand of e to the x, that's just going to become e to the x and then plus c, right? So e to the x is the same when you differentiate it, but it's also the same when you integrate it apart from this plus c. Alright, so this one also pretty same. Then the trigonometric functions, they're also pretty intuitive. They're pretty. So if I have the derivative of sine, now remember, what function should I differentiate to get sine? Well, that's going to be negative cosine, like that, plus c. And then if I have cosine, so the trigonometric functions kind of go the other way around. So that's the antiderivative of the cosine is going to be, sine of x plus c. So I'll quickly mark down the trigonometric things. So I have start, for example, with sine, then I go to cosine, and I go to negative sine, and I go to negative cosine. So one way around the circle will be differentiating. So this will be differentiating. If I differentiate sine, I get cosine. If I differentiate cosine, I get negative sine. Differentiating negative sine gives me negative cosine. And negative cosine, the derivative becomes sine. But if I take integrals, then this flips around, right? If I take the integral of sine, I get negative cosine. Take the integral of negative cosine, it gives me negative sine. Negative sine becomes just regular cosine, and then cosine becomes sine, right? So this is integral, integrating, and the other way is differentiating, like that. So this is kind of a neat way to keep track of all the different trigonometric calculus identities, if you will. because they can kind of be mixed up, right? When you have negative sign, when you have, you know, things like that. So if you have it in this neat circle, then you will always hopefully do it correctly. Alright, so the last integral rule has to do with the natural logarithm. So what function do we differentiate to get the natural logarithm? Now this one isn't as straightforward as the other ones. And the proof for this I'll show maybe a little bit later on in a different episode. But the function we differentiate will be x times ln x minus x plus c. And actually I want to make sure that that's correct, right? So say you have completed some integral or some indefinite integral and you want to make sure that you got it correct. Then what you can do always is just differentiate this function, right? So because if you have the derivative, let's see, the dx, this stands for the derivative of the integral of some function f of x dx, then this will always come out to be the original function, because if you have the antiderivative and then you apply the derivative, that just gives you the same thing, right? They're inverses. Same thing as if you were to, for example, do times, so you have 2 times f of x, and then I divide by 2, right? I apply 2 times and then divide by the inverse, and that just leaves me with 2x of f of x. So 2 and 1/2 are inverses of each other. Now this is actually quite a significant fact. It's called the fundamental theorem, here we go, of calculus. And it's actually the thing that Newton and Leibniz first discovered, right? So differentiating was around before their time, but then they discovered integration and discovered that it was the derivative's inverse, like that. Alright, so we can check that this antiderivative for the natural log is correct by differentiating this part, right? So we want to differentiate x times ln x minus x and making sure that that actually comes out to be the natural log. Alright, so let's do this. So this should hopefully be familiar. So first of all, I'm going to factor out an x, so that's going to be x minus 1, and still add on a c. And then I'm just going to use the product rule. So I have the same here. Obviously this c that vanishes, right, because it's just a constant. So the product rule. So that's the first part. Copy that, and then I have to differentiate the second part. That's going to be 1 over x. That negative 1 goes away, and I have to add on to that the other bit. Let's see. And then I have to add on to that the derivative of x. That's 1. Multiply by the, just copy ln x minus 1, like so. I'm multiplying this out, this just gives 1, x divided by x, and this is going to give me ln x minus 1, and that indeed is ln x. So this function is actually correct. I mean, I wouldn't give you an incorrect function, right? But this is just a way to check that you've done it correctly. Alright, so now I want to take a look at just a very basic integral example. So let's try to see what's the integral of, let me think here, negative 3 times sine of x dx. So this is the way that you'd usually see it written, with the function inside. Alright, so first of all I want to make use of the fact that we can bring this negative 3, we can bring that out front. It's just a constant, right? And then we're just left with sine of x dx. And that's going to be negative 3, copy that. And then sine of x dx, we can just look that up. Sine of x dx, that's negative cosine of x. Negative, or actually that 3 now becomes positive. 3 cosine of x, and I have to add on the c. Never forget that. Alright, so that's a pretty basic example. Another one we can do is, let me think, I'm just making these up really. Oh yeah, 1 divided by the square root of x dx. So similarly to when differentiating, you can write this as a power of x, right? We can write this as x to the power negative 1/2. And then we can just apply the polynomial rule, where we divide by the new power. So the new power will be negative a half plus 1, which will be just a half. So we have to divide by a half, and then multiply by x to the power of the new power, right? Add on c. Now 1 divided by a half, that's 2. X to the power of a half, that's square root x, and onto that c like that. So that's the way, well, that's basically indefinite integrals. I mean, there are a few more rules than just these, because for example, you can't differentiate or you can't integrate something like this, right? You can't. That's very hard to do. I mean, you're not going to be able to do it with just these rules that I've showed you right here. There are a few more rules. There's kind of the equivalent product rule, which is called integration by parts, and I will cover these in future videos. Integration by parts. It's kind of the product rule, but then for integrals, right? And it's a little bit more involved than the regular product rule. So it's integration by parts, and then we have something called U substitution, and it's kind of the equivalent chain rule, though again a little bit more involved. And you have some trigonometric things you could do with substituting in trigonometric functions, 1 divided by cosine squared, something like that, right? And well, there are a few more things you could do, partial fractions, something like that, right? But that's all for in the future, because I'm ending this video here, partial fractions. So I hope you learned something. So these rules, they're really just practice, right? You have plenty of examples online to practice with these simple rules. You have the constant rule, the addition rule, all of that, and never forget your plus c. Alright, thank you for watching, and bye bye.